So in this video, we're going to be talking about transformers, which are electronic gadgets that are used to step up or step down AC voltage. And take note, we are saying AC voltage, so they only work with alternating current. So how do they work? A transformer consists of a primary coil and a secondary coil. The primary coil is connected to a source of AC voltage, and it works according to Faraday's law, where there's going to be an induced magnetic flux as your AC current moves through that coil. So as our AC current moves through the coil, there's going to be an induced flux over time. So you know that alternating current is always changing direction. So our magnetic flux is also going to be fluctuating and also changing direction over time. So what happens if we put another coil, the secondary coil, close to this primary coil? It's going to experience this magnetic force, and that magnetic force is going to be transferred into that secondary coil, and hence it's going to induce an EMF in that secondary coil. Remember, this magnetic force or flux is always changing. So it's changing over time because our AC current is changing. Therefore, what's happening in the secondary coil would be similar to what you do when you are pushing a bar magnet into that coil and out of that coil continuously and fast enough such that there's going to be a change in magnetic flux. So a current is going to be induced in the secondary coil. So however, we should know the relationship between the voltages and also the current that's going to be induced. So we're going to be focusing here on the voltage. So this would be what will be happening as your AC is changing direction. The magnetic flux that's created in the primary coil is going to be changing over time, and that's going to be transferred to your secondary coil if it's close enough, and an EMF is going to be induced in your secondary coil. So you can see that there's no actual contact between these coils. So this forms the basis of wireless charging, which is now popular these days. So we just need to put these coils close enough. But you see later on that we also have to introduce a component that would make the transfer of this magnetic flux efficient. So let's talk about the relationships between the voltages there. So this is just to emphasize that in other cases, you cannot connect your device directly to the main supply because, for example, our main supply here in Zimbabwe is around 240 volts. So if you want to operate a gadget that requires 9 volts or 12 volts AC, you can't connect it directly. So you need a transformer to either step up or step down your voltage. Okay, so you know that induced EMF is going to be your change in magnetic flux with respect to time. So let's call the number of turns in the primary coil NP, and if we do so, the voltage there is going to be equal to the number of turns times the induced voltage, or the voltage that's coming from your source. So number of turns times the voltage that's coming from your source. So this is the voltage that is in the primary coil. And if we call the number of turns in the secondary coil NS, then the voltage experienced there is going to be the number of turns times the EMF that's coming from your primary coil. So it turns out that the ratio in the number of turns is going to determine the ratio of the voltages that are experienced in both these coils. So that would be the relationship between the voltages and also the number of turns in the coils. So if you wanted to know the voltage that's going to be out in your secondary coil, you can just multiply both sides by Vp there. So you see that there's a ratio there of the number of turns in the secondary coil to the number of turns in the primary coil. That factor times the voltage in the primary coil is going to be equal to the voltage in your secondary coil. So what's important is the number of turns. This is the factor that's going to make to differentiate the primary and the secondary coil voltage. Remember that the secondary coil voltage is the voltage coming from your source. Okay, so if the number of turns is large, you're going to realize that our factor is going to be large. Our NS over NP is going to be large. Therefore, the voltage experienced in the secondary coil is going to be larger than the voltage that was in your primary coil. Hence, it becomes a step-up transformer. So this is the situation that's shown there on the diagram. You can see the number of turns there in the secondary coil seem to be larger. And hence, the voltage is going to be multiplied by a factor, NS divided by NP. And this gives us our output voltage. So it's a step-up transformer, which may be useful in gadgets that require a supply of voltage larger than the one that's supplied on your mains, for example, microwaves. And when your number of turns in the secondary coil is smaller than the number of turns in the primary, then it becomes a step down. So the factor there decreases times your electromotive force from the source. Then this is going to be equal to a lesser voltage. Actually, it's the electromotive force in the primary coil. Okay, so to make the transfer of, so that's an example of a step-down transformer, which can be used to charge our phones, etc. So in order to make the transfer of magnetic flux or magnetic force efficient between the two coils, an additional component is added to transformers, which is called a ferromagnet. That's going to make sure there's efficient transfer of your magnetic flux from the primary coil to the secondary coil. So that is how it works. It's going to make the transfer of magnetic flux efficient between the two coils. So basically, this is what you have to know. You need to appreciate that the voltage in the secondary coil is going to be affected by the number of turns in the secondary coil versus the number of turns in the primary coil. That factor, NS divided by NP, times the voltage in the primary coil is going to be your output voltage. So hopefully this will propel you into understanding more about electronics. So next would be rectification of AC current. So you realize that we can use these transformers to actually power up gadgets that require DC current or DC voltage. So if you check your phone, for example, the battery inside is a DC battery. Most of our appliances require DC current. So that means we also have to turn that output voltage and current from our secondary coil into a direct current voltage. So this is done by means of diodes and by means of rectifiers. So we'll look into rectification in our next video.